OSPF is built around automatic neighbor discovery. You connect a router, enable the process, and it immediately starts looking for peers. But on a transit or broadcast network, that efficiency becomes an operational vulnerability. By default, any device running OSPF on the same subnet will automatically attempt to form an adjacency. There is no vetting process. A rogue device connects to a central switch. Trusting by default, the network allows this node to flood the segment with malicious link state advertisements. Legitimate traffic follows the compromised routing table, rerouting packets into a black hole, or silently intercepting. To stop this, the protocol uses OSPF Authentication. This mechanism forces routers to cryptographically verify a neighbor's identity before accepting a single LSA. It is critical to understand what this feature actually does. It does not encrypt user data payloads. As we pan across this physical cabling, the terabytes of web traffic, emails, and database queries flowing through the network remain exactly as they were. Authentication strictly secures the control plane. It ensures that the routing updates defining the paths through the network come only from trusted, configured peers. Securing the physical link with firewalls and access controls means very little if the logical routing table can be hijacked by a single unauthenticated hello packet. The rules of this security exchange are dictated by the OSPF packet header. Inside this packet structure, the mechanism is controlled by a 16-bit authentication type field. A value of 0 represents null authentication, the out-of-the-box state. A value of 1 indicates clear text authentication, requiring two routers to present a matching password to form an adjacency. Type 1 carries a fatal flaw. The password is sent unencrypted inside every hello packet. Anyone with a basic packet sniffer on the network segment can passively capture the exchange. In this Wireshark capture, you can see the plain text password Cisco123 clearly visible in the expanded OSPF payload. With that string, attackers configure rogue routers, match the authentication parameters, forge valid OSPF packets, and hijack the routing domain. For protecting transit links, network engineers use Type 2 MD5 cryptographic authentication. Implementing Type 1 authentication creates a dangerous false sense of security. Cryptographic hashes remain the only viable operational choice for authenticating neighbors. The premise of Type 2 authentication is that the actual password never crosses the wire. Instead of sending the password, the router relies on a one-way function. The OSPF packet data and a shared secret key funnel into the MD5 algorithm. The algorithm outputs a unique 128-bit hash, which is appended to the outgoing OSPF packet. On the receiving end, the peer router takes the incoming packet data and combines it with its own locally stored secret key, running them through the exact same MD5 algorithm. If the locally computed hash perfectly matches the hash attached to the received packet, the identity of the source is verified. Hashing stops attackers from reading passwords, but it doesn't stop them from recording a valid packet and retransmitting it later to confuse the network. Type 2 solves this by embedding a non-decreasing sequence number into the cryptographic data. If a router receives a packet with an older sequence number, it drops it, preventing the replay attack. This mechanism shifts network security from simply sharing a secret to mathematically proving you know the secret without ever revealing it. Translating protocol mechanics into a live environment requires specific Cisco iOS CLI commands. OSPF authentication requires a strict two-step configuration process. On the right, the logic tree dictates we must define the authentication type, then the key. Step 1 defines the type at the area level. Under the OSPF process, we enter Area 0 Authentication Message Digest. This command dictates that all OSPF interfaces in Area 0 must now expect Type 2 packets. Step 2 defines the specific key. Moving to the interface level, we enter IP OSPF Message Digest Key 1 NG 5. Followed by the password. The number 1 in that command is the key ID parameter. Key IDs allow network engineers to configure a second key on the interface. The router will send packets using the new key while still accepting the old one, letting you seamlessly rotate passwords without dropping the live OSPF adjacency. The CLI operates on a strict configuration hierarchy rule. Interface-level configurations will always override area-level configurations. If one specific interface requires a different authentication type than the rest of Area 0, configuring the type directly on that interface takes absolute precedence over the area command. The syntax physically enforces the theoretical two-step rule, establishing the interface as the ultimate authority in OSPF behavior. In practice, you will encounter situations where the passwords match perfectly, but the routers refuse to form a full adjacency. The neighbor relationship gets stuck in the init state. A router is receiving hello packets, but dropping them before adding its own router ID to the reply. To find the exact mechanism of the drop, we check the internal logs. This terminal output displays the result of a debug IP OSPF adjacent command. Mismatch authentication type. Input packet specified type 2. We use type 1. The routers are configured with mismatched off-type variables. One expects an MD5 hash, the other expects clear text. The adjacency fails immediately, before the passwords are even checked. The second most common failure point is a mismatched key, caused by hidden syntax errors. An invisible trailing space typed at the end of a password string in the iOS configuration changes the resulting MD5 hash completely. The protocol continues to evolve. Modern iOS XE environments now support Type 3 HMATCH SHA authentication, and OSPF version 3 delegates authentication entirely to IPsec. Securing the control plane requires strict alignment of authentication types, mathematically synchronized keys, and a firm grasp of the interface override hierarchy.